Welcome to the deep dive. Today we're looking at something you probably encounter more often than you think, X-rays. From your doctor's office, airport security, even checking welds on pipelines, they're everywhere. But how often do we really stop and think about the physics and the engineering that make them possible? Okay, let's unpack this. Our mission today is to really get into the heart of X-ray technology. First, the fundamental principles, how are they even generated? And then we'll look at the actual hardware, the basic generator construction, sort of a behind-the-scenes tour.
And it's a really important area. I mean, modern electronic X-ray sources are incredibly versatile, way beyond older methods. We've seen huge leaps, especially with solid-state components coming in. They've really tackled those old issues, size, weight, durability concerns. That's why interest just keeps growing.
Makes sense. Okay, let's kick off with part one, the invisible force X-ray physical principles. I guess the story starts back in 1895, right? Wilhelm Röntgen.
That's the one. He stumbled upon this mysterious radiation, didn't know what it was, so he called them X-rays. The X for unknown.
Huh, clever. And we now know they're electromagnetic radiation, like
Wow.
light, but different.
Exactly. Super short wavelengths. And the key thing, the really crucial part, is that they're ionizing.
Ionizing. What does that mean in practice? Why is it fundamental?
Well, ionizing means the X-ray photon has enough energy, packet of energy, to knock an electron right out of an atom it hits.
Yeah.
Creates an ion, a charged particle. It's a powerful interaction. And the principle behind making them, it boils down to conservation of energy. Basic electromagnetic theory predicted this. If you decelerate a charged particle fast enough, it's got to radiate energy.
So you take fast electrons.
Right, typically electrons, yeah. You accelerate them at high speeds and then slam them into a target material. They stop, or at least slow down dramatically.
And that releases the energy as X-rays.
Well, some energy. Here's the kicker. Most of it, like over 97%, just turns into heat.
97%, wow.
Yeah. So getting rid of that thermal energy, that's a massive design challenge for any X-ray generator. Absolutely critical.
Okay, so that tiny fraction, less than 3%, that's our useful X-rays. What's happening there atom-wise, this breaking radiation idea?
Right. Here's where it gets really interesting. As those high-speed electrons zip past the nucleus of an atom in the target, the nucleus's positive charge pulls on them, slowing them down, deflecting them. It's that rapid deceleration, that braking, that causes the electron to lose some energy by emitting an X-ray photon. Hence the name. Exactly. It's called Bremsstrahlung, German for breaking radiation. It fits perfectly, and this process creates a whole range of X-ray energies, a continuous spectrum.
And we measure these energies in kV.
Yep, kilo-electron volts, keV, or mega-electron volts. 1 keV is the energy an electron gains when accelerated through 1 kilovolt of potential difference. So that voltage between the cathode, where electrons start, and the anode, the target, is key.
Got it. So the voltage gives the electrons their punch. But you mentioned earlier there's not just this continuous spectrum, there are also these spikes, intensity spikes.
Ah, yes. What's fascinating here is these are the characteristic X-rays. They're generated differently. It's not just breaking near the nucleus. Here, the incoming high-speed electron actually collides with and knocks out one of the electrons orbiting the target atom, one of the tightly bound ones.
Okay, so it's a direct hit on an orbital electron.
Right. Think of the atom like a mini solar system nucleus in the middle, electrons in specific energy shells or orbits around it.
Like planets.
Sort of, yeah. When an inner shell electron gets knocked out, it leaves a vacancy, a hole. An electron from a higher energy shell further out immediately drops down to fill that hole.
And that releases energy.
Precisely. But because these energy levels are distinct and specific for each element, the energy released when that electron drops down is also very specific, a discrete amount. It comes out as an X-ray photon with an energy that is characteristic of that target material.
Ah, so each material has its own unique set of characteristic X-ray energies.
Exactly. It's like an atomic fingerprint. Super useful for identifying materials using techniques like X-ray diffraction, or for creating beams that are almost monoenergetic. Nearly all the X-rays have the same energy.
That fingerprint idea is great. Really clear. Okay, but where do all these initial electrons come from before they even get accelerated?
Good question. That process is called thermionic emission. It's surprisingly simple in concept. You just heat a piece of metal, usually a tiny tungsten filament, in the X-ray tube until it glows red hot.
Like an old light bulb filament.
Very similar, yeah. When it gets hot enough, some of the free electrons within the metal gain enough thermal energy to literally boil off or escape from the surface.
And they just hang around.
Initially, yes. Without any voltage applied, they just form this sort of cloudy space charge right near the filament. But as soon as you apply that high voltage, that potential difference between the cathode and
I'd
anode,
get pulled across.
instantly, they're rapidly accelerated towards the anode, forming the electron beam that will generate the X-rays.
Okay, so electrons generated, accelerated, hit the target, make X-rays, both Bremsstrahling and characteristic. What happens next? When the X-rays actually go through stuff, that's absorption.
Right, exactly. X-ray absorption.
Yeah.
Crucial concept. As X-rays travel through any material, their intensity decreases. They get absorbed or scattered, and this happens exponentially. The further they go, the more get absorbed. Think of it like IOEX. Intensity drops off.
And does it depend on the material?
Oh, absolutely. It depends strongly on two things: the energy of the X-rays themselves and the density and atomic number of the material they're passing through. Lower energy X-rays get absorbed more easily. Denser materials absorb more.
Right.
And if we connect this to the bigger picture, understanding absorption is vital. It dictates what materials you can use to build the tube window, how you filter the beam to get rid of unwanted low-energy rays, and critically, how you design shielding for safety.
So it affects image quality and safety.
Everything from how clear your medical scan is to protecting the operator.
Makes total sense. Okay, we've covered the physics, the invisible forces. Let's shift gears now, part 2. Bringing the X-rays to life-basic generator construction. This is the engineering side.
Right, where the physics meets the hardware.
So a standard X-ray generator, what are the main bits?
Broadly speaking, 3 main components. You've got the X-ray tube itself, the heart of it all. Then you need the high voltage source to provide that accelerating potential. And finally, the control equipment to manage the whole process, timings, currents, voltages, all that.
And tubes have changed a lot over time.
Dramatically. Early tubes were gas-filled, kind of unreliable. Modern tubes are high vacuum, much more stable, longer lasting, and way more compact.
Okay, let's break down that tube. The envelope first, the outer casing.
Sure. The envelope holds the vacuum. Older ones were often glass.
Like glass breaks.
Yeah, susceptible to thermal shock, mechanical shock. Not ideal, especially for industrial use. So now, many are metal ceramic tubes. These use a metal cylinder, often Kovar or stainless steel, with ceramic discs, usually aluminum oxide, brazed on the ends.
Why ceramic?
Excellent electrical insulator, very strong, handles heat well, and you use special high-tension grease at the connections. This whole design allows for much better insulation in a smaller space, which is key as you go to higher energies.
Inside that, we have the cathode with the filament.
Exactly. The cathode assembly holds the tungsten filament. It's heated by a separate low-voltage AC circuit. That's what provides the electrons via thermionic emission. Filament currents are usually maybe 1 to 10 amps.
And the tube current, the electrons actually crossing the gap.
That varies hugely depending on the application. Microfocus units might be under 300 microamps. Conventional radiography tubes can be over 20 milliamps. Big difference.
Now, getting a sharp image needs a tiny source point, right? So beam focusing is critical.
Absolutely critical. It relates directly to something called geometric unsharpness. Basically, the bigger your X-ray source spot, the fuzzier the edges of the shadow or image will be, like using a big light bulb versus a tiny LED to cast shadow.
So how do you focus that electron beam?
Several ways. The most common is the focusing cup. The filament sits inside a small recess in the cathode structure. This cup is shaped to create an electric field that kind of pushes the electrons together, repelling them from the sides, focusing them into a tight beam aimed at the anode target.
Clever. Are there other methods?
Yeah, another neat trick is line focusing. You actually produce a rectangular electron beam, maybe longer than it is wide, but you angle the target face, say around 21 degrees relative to the beam. When you look at the target from the side where the useful X-rays come out, that rectangle appears foreshortened into a much smaller square. It's an effective focal spot.
Ah, like looking at a rectangle edge on makes it look like a line.
Sort of, yeah. It lets you spread the heat over a larger actual area on the target, but still get the imaging benefit of a small spot. Typically 1 to 3 millimeters for the effective spot. You can also use deeper focusing cups, sometimes called a screen effect, to strip out lower energy electrons from the beam edges, making it even sharper, though it costs you some output power.
And for really tiny spots,
Sure.
like microfocus.
Then you get more advanced. Triode arrangements add a third electrode, a grid or bias cup, with its own negative voltage. This gives much finer control, allowing focal spots down to, say, 10 micrometers. Some systems even use electrostatic or magnetic lenses, like in an electron microscope, to focus and even deflect the beam. Deflecting lets you steer the beam to different parts of the target, spreading the wear and tear, extending tube life.
Amazing precision. Okay, let's talk about the other side, the anode and target. We know heat is the big issue here.
The dominant issue, remember, over 97% heat. If that heat isn't managed, it just destroys the target surface. It erodes it, makes the focal spot fuzzy, reduces X-ray output, and ultimately causes the tube to fail.
So what are anodes made of?
Usually a material with really high thermal conductivity, like copper, to pull the heat away from the focal spot quickly. The actual target material, the bit the electrons hit, is often a small insert of something like tungsten embedded in the copper.
In cooling. How do you get the heat out of the anode?
Depends on the power level. For low power or intermittent use, just radiating the heat from the anode structure into a surrounding reservoir of insulating oil or gas might be enough. But for high power, continuous operation, you need active cooling. Often the anode is hollow, and you pump coolant water, oil, directly through it.
So what does this all mean? It means a huge amount of engineering is just focused on stopping the target from melting.
Pretty much. And a brilliant solution for higher power is the rotating anode.
How does that work?
Instead of a fixed target, the target is a disc, usually tungsten or the tungsten alloy, mounted on a rotor. This disc spins at high speed, thousands of RPM, during the exposure.
So the electron beam hits a constantly moving surface.
Exactly. It spreads the heat load over the entire circumference of the disc's track, not just one tiny spot.
That must make a big difference.
Huge. It allows you to increase the tube current, the electron flow, by maybe 10 times compared to a stationary anode of the same focal spot size. This means you can use much smaller focal spots, under a millimeter, for shorter exposure times. Absolutely essential for medical imaging, stopping motion blur, and for some high-res industrial stuff.
Makes sense. And the target material itself, does that change?
It can. Tungsten is common for general radiography because it has a high atomic number, which is efficient for Bremsstrahlung, and a very high melting point. But for analytical applications like X-ray diffraction, where you want those characteristic X-rays we talked about, you might use copper, iron, cobalt, molybdenum targets.
And the angle of the target face matters too.
Yes, that angle, typically 0 to 30 degrees, affects the effective focal spot size, like with line focusing, and also how the X-rays are distributed in space. A common angle is around 20 degrees, which tends to send most X-rays out perpendicular to the electron beam path.
You also mentioned beam shape, conventional versus Gaussian.
Right. Most conventional tubes aim for a uniformly intense electron beam hitting the target. But for microfocus work, where you need to resolve really fine details, a Gaussian or bell-shaped intensity distribution across the focal spot can actually provide better definition for closely spaced objects.
Okay. What about the other structures around the target, like the hood?
The hood, usually made of copper, sits around the target. It does a couple of things. One, it intercepts stray electrons and absorbs unused X-rays that aren't going out the window towards the subject, helps clean up the beam. Two, it acts as an electrical shield, protecting the tube's insulating components from scattered electrons or photoelectric effects that could cause arcing.
Does it block the useful beam?
No, it has an opening, often covered by a thin beryllium window. Beryllium is used because it's very low density and has a low atomic number, so it absorbs very few X-rays while still being strong enough to maintain the vacuum and stop any stray electrons. Sometimes heavier metals like tungsten are built into the hood to absorb stray high-energy X-rays more effectively.
And the rod anode. You mentioned that earlier.
Yeah, the oxtail design. It's a specialized tube where the anode structure is long and thin, allowing it to be inserted into tight spaces, like inspecting inside a pipe weld. A key feature is that the anode itself is usually grounded, simplifying connections and cooling, which is often done with water flowing through the rod. They've been somewhat superseded by compact metal ceramic tubes now, but still used in some cases.
Okay, so we have the tube insert. How is it cooled and housed?
Right. The tube insert itself sits inside a larger housing, the tube head. And the space between the insert and the housing is filled with an insulating coolant.
Oil or gas?
Usually a special dielectric oil or gas like SF6. They have to be great electrical insulators as well as transferring heat.
How does the heat get out of the coolant?
For lower power units, simple convection currents within the oil might move heat to the outer casing, which then radiates it. For higher power, you need active circulation. A pump moves the oil or gas through a heat exchanger, like a radiator, often cooled by fans or water.
And you mentioned bellows for oil.
Yeah, oil expands significantly when it heats up. So you need an expansion bellows, usually made of metal or resistant rubber, to accommodate that volume change without building up pressure. Gas-filled heads don't need bellows because the gas is compressible, but they usually have a pressure gauge to ensure the insulating gas hasn't leaked.
And this all sits in the tank head.
Correct. The tank head is the robust outer casing. It provides structural support, contains the coolant, holds the electrical connectors, supports pumps or fans, and, crucially, incorporates lead shielding to absorb stray radiation.
So it's protection, cooling, and structure all in one.
Exactly. And in some designs, called tank units, the high-voltage transformer and the filament transformer are also housed inside the tank head, along with the tube, making for a very compact, self-contained system.
Okay, let's talk about that power. The high voltage sources, we need huge voltages.
We do. We're taking standard mains voltage 100, 240, maybe 460 volts and stepping it up massively, anywhere from 5 kilovolts, so 5,000 volts, up to 420 kilovolts or even higher for some industrial units.
How did they do that initially?
The simplest circuits were self-rectified. Basically, the X-ray tube itself acted like a diode, only allowing current to flow when the anode was positive relative to the cathode during the AC cycle.
Sounds simple, but maybe risky.
It was. The big risk was tube backfire.
Yeah.
If the anode got too hot, it could start emitting electrons itself, leading to current flow in the wrong direction, potentially damaging the tube or transformer. Used mainly for lower power units, maybe 50 to 300 kilovolt peak, a few milliamps.
So improvements came with rectification.
Right. Adding diodes, vacuum tube diodes initially, now solid state to convert the AC from the high voltage transformer into DC before it gets to the X-ray tube. This gives rectified and filtered circuits. You often add capacitors to smooth out the voltage ripple, providing a more constant potential difference. The transformer might be in a separate tank in these setups.
Any specific circuit designs?
Several common ones. The Villard circuit is a voltage doubler. The Great circuit provides full-wave rectification, more efficient, very common in medical systems. And then there's the Greinacher circuit, often called a constant potential circuit. It's basically a cascade voltage multiplier.
Constant potential, does that mean constant energy X-rays?
Common misconception. It means the accelerating voltage applied to the electrons is kept very close to its maximum value throughout the whole AC cycle, very little ripple.
So the electrons hitting the target are nearly monoenergetic.
Exactly. The electron beam energy is nearly constant. This is great because it boosts the output of high-energy X-rays and significantly reduces the number of low-energy X-rays, which often just contribute to patient dose or scatter without improving the image.
What's the benefit?
Big benefits. Enhanced high-energy output, much shorter exposure times, maybe 30% less, and often longer tube life because the heating is more consistent. But remember, the X-rays produced via Bremsstrahlung are still a spectrum, not monoenergetic, because the deceleration process itself is random.
Okay, that's clear. And how the circuit is grounded matters too.
Yes, grounded circuit configurations offer different advantages. Cathode grounded means the cathode and filament circuit are near ground potential. This allows the filament transformer to be external, often in the control unit, making the tube head smaller and lighter, common for lower kV units. Center grounded effectively halves the voltage each end of the tube sees relative to ground. This reduces the insulation required in the high-tension transformer, making units smaller, especially in the 200-420 kV range. Anode grounded is used with those rod anode tubes or some metal ceramic designs. It simplifies target cooling, as the anode is at ground potential, typically used from 30 to 200 kV.
Are there other designs too?
Oh yeah. Modern systems might use higher frequency power supplies. Running the transformer at kilohertz instead of 50 or 60 hertz allows for much smaller, lighter transformers and smoother output with less ripple. Some use three-phase input power for better stability or generate almost square-wave high voltage for extremely low ripple. Lots of innovation there.
Fascinating how many ways there are to power these things. Finally, connecting it all up. High-tension connections. Sounds tricky with those voltages.
It is a major challenge, especially when the tube and transformer are separate units. You need specialized high-voltage cables.
Shielded, I assume.
Definitely shielded. But the real weak point is the termination, where the cable connects to the tube or transformer housing. These connections use plugs and receptacles made from insulating materials like phenolic resins or increasingly ceramics. They're often filled with insulating epoxy resin to exclude air.
Why is excluding air so important?
Because air is a relatively poor insulator compared to solid materials or oil. Any air gaps significantly reduce the voltage the connection can withstand before arcing over. For air, the breakdown strength is roughly 10 kVs per 10 millimeter gap, which isn't much when dealing with hundreds of kilovolts. You'd need impractically long connectors if you relied on air gaps.
So filling with epoxy helps.
It helps, but ceramic insulators have been a huge step forward here. Ceramics can be precisely machined to create very flat, rigid mating surfaces. When you join these surfaces, often using that special high-tension grease, you can effectively exclude almost all air from the critical high-voltage interface.
So less air means.
Means you can make the connections much shorter for the same voltage rating. This has allowed for substantial decreases in the overall size and bulkiness of high-energy X-ray units, making them much more practical, a really key innovation.
Wow, what an incredible journey we've taken. From Radon's discovery of a mystery ray,
Right, back in 1895.
all the way to these incredibly complex, precisely engineered machines we use today. It's this amazing mix of deep physics principles and just really clever practical engineering.
It really is. When you think about it, controlling electrons with such precision, generating these powerful rays, managing immense heat loads, handling hundreds of thousands of volts, the level of sophistication is, well, it's astounding. A key insight, I think, is just how much intricate design goes into making what seems like a simple beam of energy safe and effective.
And that insight itself. Well, this raises an important question,
What's that?
maybe for you, our listener, to think about. We've seen how these core ideas, energy conversion, material science, clever construction, make X-rays work. But how do these same fundamental principles pop up in other technologies you rely on every day? And looking forward, what might be the next big leap for this technology? It's over a century old, but clearly still evolving. Will it be even smaller units, more efficient energy use, maybe radically new ways to shape or steer the beam?
Lots to ponder there.
Definitely. Something to think about. The potential is still enormous.